Well, I'm sure all Korean audience in this room knows me, right? Well, as Professor Choi introduced me, I'm very well known, believe it or not. Okay, when I first invited by Professor Choi, well, the invitation is still going on. Well, it doesn't work. Okay. Okay. Okay, when he first invited me, I had no idea who you will be. So I will start from introduction of myself. Well, believe me, I'm a physicist, and this is my Google Scholar page. So, well, it wasn't that bad, even though it wasn't too good. Anyway, what I'm trying to tell you is that I am like a physicist to the bone. I'm a physicist. And for about 10 years ago, I began to write books for public. And so far, I wrote 10 books, and the first 2 books were about my research. And it is about explanation of my research to Korean public, and strangely, it was kind of successful. So I just keep publishing other books. So far, I had 10 books, and the last one is about my YouTube channel. And at the same time, I'm running my YouTube channel. And the Korean name for my YouTube channel is 범준의 물리다. And it has actually double meaning. In Korean, 물리 means physics, or it's like a bite. So the 범준의 물리다 means like you are bitten by me. So you cannot escape. Or I think also the English pronunciation can be interesting. It's like 범준's physics bite, right? So it makes sense somehow. And surprisingly, even though I started my YouTube channel a little bit less than 2 years ago, so far, I checked this number today morning, and it was 270,000 subscribers I have. And I have now about 100 video content, and the total number of my viewers is like 26 million. This number is very surprisingly large if you compare with the Korean population. It is 50 million. So it's like 1 of 2 Korean people watched my video. And it was very unbelievably large number. Okay, so I dealt quantum physics in my contents a few times. And so this is a snapshot. And surprisingly, people like them. I feel it very strange. Why? So I think the topic of my talk today is like demystifying. I think one of the reasons why people like this content about quantum physics is that they have this illusion or some mysterious thinking, and they really liked it, this aura of the quantum physics. That's what physics like, what people like. So I started from the physicist, and of course, I started to write papers. And after that, I began to publish books, and now I'm running my YouTube channel. So this is the summary of my short journey. Well, I can proudly say that one of my papers was cited more than 2,000 times. I think that's not a small number. So I'm very proud of it. But we all know that it really means that they read my paper all. So just think of your very recent publication, and I'm sure you will have like 30 or 40 references as a list. But close your eye and raise your hand if you read all the papers in your reference list. We didn't. But when I wrote book, and my first book was sold by more than 30,000 copies. And interestingly, we don't pay to read the papers, but people buy the books. So financially, it's a kind of much better than writing paper. I don't care if they read or not, but anyway, they pay. Okay, so conclusion so far is books are much better than papers. Yes. And now I'm running my YouTube channel. And one of my contents was viewed by more than 1 million people. So, conclusion, you need to run your YouTube. Okay, so efficient way to disseminate his knowledge to public. So we can think of papers, or public books, or running YouTube channel. I think books and YouTube, if you compare, YouTube is much better, and books are much better than papers. But don't agree with me. Of course, all these different media have different audiences. So my experience so far is that people who read books, then they don't read papers. And interestingly, people who watch YouTube, they don't read books. So it's like a very different market. So when I first started my YouTube channel, and I recognized that maybe my book will be sold much more than before, but it doesn't change at all. So it's like people consume this science knowledge in two completely different ways, and they don't overlap to each other. So I think it's a very, very big task for all of us. How can we extend all those people who consume science knowledge in YouTube? How can we make them read the physics books? Maybe not to papers, but at least for books. I think we need to try very hard. Okay, so far it's about me. So what I'm doing and what I did. Okay, then the second part of my talk will be about my experience about when I explain quantum physics to public. And the most typical, the hurdle or barrier is this difference between particles and waves. Okay, I think everyone knows. I'm sure I don't need to explain you, but I like to explain these concepts, assuming that you are general public, and to see what I tell to Korean public when I explain the quantum physics. Okay, ping pong and sound. The particle, well, particles is like apples, right? So you have one apple, and next to it, we have another apple. Of course, we can pinpoint where exactly the apple is. And also, if you have one apple and second apple to next it, of course, in total, we have two apples. So the particles we can add. 1 plus 1 becomes 2. But waves are completely different. You cannot tell where the wave is. Just look at this animation. When we tell this is a wave, it doesn't mean that we are pointing one specific point. The whole thing is a wave. So wave, we can specify the position. And interestingly, wave we can add as we add 1 apple plus 2 apple. But when we add 2 waves, sometimes they can be twice bigger. So 1 plus 1 can be 2, or sometimes they can cancel. So 1 plus 1 can be 0. So when I explain this concept of particle and wave, people just intuitively, they know it. But the waves, they don't. They actually have some problem about what is wave. So you have first the hurdle when you explain this particle and wave. Okay, so of course, in our classical world, composed of only big things, then we can always tell the difference between particles and wave. If something is particle, that something cannot be waves. If something is wave, it cannot be particle. So there are very clear divide line between particle and wave. Okay, the next topic I usually use to explain this difference between particle and wave is by using this famous double slit experiment. So if we throw ping pong ball like a particle through two slits, then of course some ping pong ball passes through the slit above, and some ping pong ball will pass through the slit downward. And of course, in the opposite side of the wall, we have two strips where we can see the ping pong balls. So this is about particles. But if we have wave, then of course they interfere to each other, and then we have this clear pattern of the interference. So when I speak about this wave interference, most audience, they never heard of it, and they never saw it. So usually I pick one of my audience and then get his hair. I really recommend it. This is very simple experiment. So I tried this many times, but strangely, men's hair is much better than women's hair. Probably some thickness difference. Anyway, so I pick one guy and then get his hair, and then just use your laser point and put the hair in front of your laser point and just give the shed light on through this hair. And this hair works like this position. So your laser light, some part will pass through above the hair, and some light will pass through lower this below this hair. And then you see this very beautiful interference pattern. They're just like this one. And you can show this small experiment in front of your audience. So I think this is a very nice experiment, very easy. But remember, men's hair is better than women's hair. And this is also, and when I have time, then I also explain that if you measure the gap between this dark area, and if you measure the distance from your hair to this pattern, and if you know the wavelength of your laser point, then this is the very accurate way to measure the thickness of your hair. Anyway, I really like this experiment, and I really recommend you to repeat the experience in front of you. Thank you. Okay, of course, the next story goes to throwing out the electrons. Okay, so this is very well-known experiment. I think everyone knows it. So this story goes like you throw one electron, and it passes through double slit, and the other side of the wall, then we have this luminescent material, and then when electron touches some position, then it blinks. It makes a small light. So we just throw one electron and see one blink, and we throw a second electron and you see another blink. And just look at the figure A. And then I ask my audience, what do you think if you look at figure A, electrons are waves or particle? Then of course everyone shouts that electron must be particle. And then I continue to explain figure B. So we just throw one electron and wait, and we throw second electron and wait. So this part must be very much emphasized. We don't throw all electrons at the same time. We just throw one by one. So electron cannot be able to interact with other electron. So what then we can explain? The wave-like spectrum, wave-like pattern in figure D. So the only way we can explain figure D is that one electron passes through two slits at the same time. And then people usually they are shocked. How can it be possible? So that well, of course, we all know that, but the people, they are really shocked by this experiment. And this time, then at this moment, I usually present my own analogy about this experiment. So I start like this one. You and me, all of us, are living in a town. And we are colorblind. We can see only black and white. So we are living in very peaceful life. But at one day, some new guy moved into our village, and he is wearing blue shirt. So we ask him about what's your color of your shirt, and he says blue. But we don't know what is blue. So we claim repeatedly that no. Our question is, what is your color of your shirt? Is it black or is it white? And he doesn't understand what's black and white. He just keeps telling us that no, my shirt is blue color. And we don't understand. So this is an analogy about the quantum world and then the classical world, where particles and waves are well separated. So in some sense, electrons are like this new guy moved into our village, where we can see only black and white. Then whose fault is that? Is it his problem or our problem? So of course our problem. We cannot insist that this guy must choose between black and white. His color is blue. So in some sense, electrons are waves and particles at the same time, or electrons are neither particles nor waves. Both are correct. Yes. But anyway, this is my analogy. When I use a lot in my public lecture to general audience. And another misunderstanding of quantum physics, I think this must be very careful. When we are talking about uncertainty and probabilistic nature of quantum mechanics, people are just very confused. And you have to know it, that when we tell the general audience that something is probabilistic, then they understand this concept as we cannot tell anything. If something is described by probability, they accept it that we don't know it at all. So you have to be very careful. Anyway, okay, then I can start from the classical mechanics. Of course, we can write down the classical mechanics equation into these two equations. And I usually tell my audience that look at very carefully and compare the right-hand side of equation and left-hand side. And inside of this parenthesis, we have this small symbol t. And that's exactly the time now, at the present. So this equation means that we know the information at present, at now exactly, that we can say what will be the information a little bit later. So this equation tells us what happens now, then what will happen 1 second later. Then of course we can repeat million times. So what does it mean? If we know all the required information exactly now, then we can tell what will happen in 1,000 years later. So this is the deterministic nature of the classical mechanics. But in some sense, Schrödinger equation is also deterministic. I think everyone knows it. The wave function described by the Schrödinger equation is determined. If we know the wave function now, we can tell what is the wave function in far future. But of course, classical mechanics and quantum mechanics are very different, because this wave function is not about actual position. It's about the probability where we can find the particle. So this is also my analogy I use a lot. So to my audience, I say, let's say I can tell you whether or not tomorrow we will have rain. And the probability I can tell you accurately. So the rain probability tomorrow is 49.89714%. So I tell this number and I ask my audience, so what does it mean? Can we know that tomorrow morning we will have rain or not? Knowing the probability exactly, it doesn't mean that we know the outcome accurately. And people are very confused about this difference. So if we have this chance to convey the quantum physics to audience, I recommend to emphasize this difference. Knowing the probability doesn't mean that we know the outcome. Okay, so the quantum mechanics is somehow deterministic, but what is determined is probability. Okay, and then I often try to explain why then, even though we only know the probability, why your smartphone works perfectly. Of course, there are so many electrons, so that knowing the probability exactly actually means that we know how many electrons are behaving in some certain way. This is a very accurate expectation we can have. Okay, the other misunderstanding or other mystery people really like is this famous Schrodinger's cat. And many people are confused about this concept, and they believe from their heart that physicists are claiming that cats can be in superposed state of life and death, but it's not, right? So we all know that from this process inside the box, we all believe that it's not possible. Okay, anyway, I think everyone knows that what the Schrodinger's original idea is to pinpoint the weirdness of the quantum mechanics. He didn't believe that the cat is both alive and dead. Okay, that's one thing. And of course, the behind the story is very profound. So this thought experiment is about what happens at exact moment of the observation, and then why then this small radioactive material follows quantum mechanics, but we cannot think of quantum mechanical superposition of the cat. Then what is the division line between small and big? So of course, this is a very fundamental question, but people are often confused about that. Physicists are really believing that cats can be at life and death at the exactly same time, but that's not true. Okay, well, okay, this is also, I show my audience a lot. So I showed my audience first this electron throwing double slit experiment, and then I ask my audience that what will happen if we throw out not electron but big things. And I show this paper. I think everyone knows this paper. So this is about the double slit experiment of this big atom, big molecule, fluorine. And this is composed of 60 carbon atoms. So the total mass of this molecule is more, I don't know, maybe million times bigger than electron. So big things, we can have this double slit experiment. And then I ask my audience, what will happen if we throw out Schrödinger cat? It's not easy, right? But in principle, we cannot assign exactly zero probability for this cat double slit experiment. Okay, so this is about what I show my audience. And usually the last slide about this Schrödinger cat, I usually show this interesting cartoon. So the inside of the box, Schrödinger cat is so much harassed by human physicists, so he is planning revenge. So he is studying quantum mechanics to make revenge to all of you physicists. Okay, and another thing I actually like to share with you is about this concept of the understanding. Understand means that we stand under. So if you need to define under, we have two things. Something is there, and under that something, we have something else. So when we talk about understanding, we are actually comparing two different things. Now, of course, when we are talking about quantum mechanics, the quantum mechanical objective world is out there. And then, what is then? This is under what? Of course, in our brain, in some sense, we have this classical worldview composed of our knowledge. I don't know, more than, million years knowledge about experiencing big things. So we have this worldview of classical mechanics, and we like to understand the quantum behavior observed outside. Of course, it's completely impossible. So no one can understand quantum mechanics in this sense. So I think everyone knows about this, what Feynman said. Nobody understands quantum mechanics. I actually don't like this sentence. This is the origin of the lots of misunderstanding by general audience. They ask me about, okay, even Feynman didn't understand anything, and he said that no physicist can understand quantum mechanics. Then how can we trust these all quantum things physicists are claiming? So but my understanding of this Feynman's sentence is that he is correct in the sense that if we compare with the objective quantum world and our classical worldview, and he is completely right, and I agree with him. But if we change the what to compare, the quantum behavior outside, and if we change our worldview inside of our brain from classical worldview to quantum view, of course it's very, very abstract and very mathematical, we know that. But if we put this new worldview, and if I ask you about, do you understand quantum physics? Then I think everyone can say yes. So this meaning of understanding, I usually try to explain my audience. So both are correct. So no one understands quantum physics, that's right. But everyone in physics undergraduate, more than third grade, then we all know and understand quantum physics. Both claims are both correct. Okay. So everything is quantum, that's my claim, because we can build big things starting from the small things. So if we understand the small thing, we can just build up to understand big thing. So quantum mechanics can lead us to classical world, but even though we have complete knowledge about big things, classical mechanics, we cannot go down to quantum mechanics. So everything is quantum. But then people often ask me, then why then all students in high school learn about free fall and projectile motion, even though if quantum mechanics is everything? And of course, we all know that directly applying quantum mechanics to big things is mathematically completely impossible. It's so complicated. So this is my final view graph when I explain quantum physics to my audience. So quantum is everything, and small part also belongs to quantum world, but for this tiny dot, we can apply classical mechanics to explain this behavior. Okay, so this is end of my talk. Okay, thank you. Okay.